Good morning, grade 12s. Welcome to our lesson on Ksp, the solubility product constant. So, solubility equilibria, saturated solutions. If a solution is saturated, that means it can be at a state of equilibrium. So we can actually then calculate a Kq value for it. Remember, when something is saturated, or when we're at any equilibrium type of situation, the rate of dissolving is going to be equal to the rate of recrystallizing. The key word here is rate. It's not the amounts that stay the same, it's the rate that stays the same. As long as we don't change things like pressure or temperature or volume, those rates will stay the same. So consider for a moment this coffee cup that we see in the picture at the bottom. In this coffee cup that we're seeing in the picture, what we're noticing that is we have solid sugar sitting on the bottom. So here we've got sugar molecules in the form of a solid. And every once in a while they'll dissolve, they'll go up into the liquid, and then that's my dissolved sugar molecule surrounded by his little cage of waters. And now he'll be in the aqueous form. Now eventually we've got so many little sugar molecules up there that some of them will start to come back down to be a solid again. So we're noticing that we have this equilibrium situation happening, where every time one molecule goes up from solid to aqueous, another one goes back down from aqueous to solid. I really got to apologize for the nature of my writing while we're trying to write on this little tiny laptop screen of mine, but we're getting the impression as long as you're listening. The neat thing that this works with that really helps us out as chemistry students is if our equilibrium is between an undissolved solute, something that's in the form of a solid, and a dissolved solute, something that's in the form of aqueous, we can remember that solids are never included in KEQ calculations of any kind. So our math gets infinitely simpler. Look at this solubility balanced equation. Suppose we were dissolving some solid silver bromide. Silver bromide doesn't dissolve very well in water. In fact, it's considered typically very insoluble, so only a very tiny amount of it will dissolve. In grade 11, we straight up called it insoluble. I was oversimplifying it for you. It's not that it doesn't dissolve at all. It's that that tiniest little bit will dissolve. So as soon as silver bromide dissolves and it ends up in the liquid, what we end up with is silver ions and bromine ions. Those silver ions and bromine ions are surrounded by little cages of water and almost immediately start to reform solid silver bromide. So this becomes an equilibrium, and we have two-way arrows because it's an equilibrium situation. My Ksp formula for this then, and Sp stands for solubility product. Again, this is just a KEQ calculation. Will be the concentration of my silver plus 1 ions times the concentration of my bromide minus 1 ions. Remember, we are multiplying here, not adding. This is not an addition. This is saying this and this are formed. This is a balanced equation. This is our math down at the bottom. Okay. How would I write the Ksp expression for magnesium hydroxide? I've got the balanced equation written for you here. This would be a great time for you to pause the video and try to see if you could write the Ksp expression on your own along the side. Go ahead and pause that video now. Are you back? Great. My magnesium hydroxide, when it goes and dissolves into solution, makes 1 magnesium ion, and from the equation here, we can see it makes 2 of the hydroxide ions. So I've written 2 of the hydroxide ions. We could picture it as this is a magnesium, and he's attached to 1 hydroxide here, and he's attached to another hydroxide here. When the water molecules come and try to pull them apart and try to form hydration shells around them, what we end up seeing is we'll end up having my magnesium ion floating around, and he will have lost both of his electrons, so he'll be +2, and the 2 hydroxide ions we know form negative ions, OH minus 1, here's another OH minus 1, and they will be all completely surrounded by hydration cells of water molecules. There's our water molecules. And so this balanced equation is explaining to us how the magnesium hydroxide broke apart into its ions. Okay, so let's take a look then at how the Ksp expression would look for this. My Ksp expression looks like this. Ksp is equal to the concentration of my magnesium plus 2 ion times the concentration of my OH minus 1 ion. And remember what we do with the 2? It goes out here as an exponent, squared. We do not put it over the concentration of magnesium hydroxide because magnesium hydroxide is a solid and we don't include solids in our equilibrium expressions. So this is always kind of nice. We don't have any denominators in any of our Ksp calculations or our expressions. Okay, how do we do the math for this? Well, if you take a minute, open up your textbook to about page 615. In your textbook on page 615, we have a big chart, and that's a solubility product constant chart. KSPs are actually characteristic properties of substances. Characteristic properties are just things you can go and look up on a chart. At any given temperature, we can go and look it up because someone's bothered to figure it out exactly how much can dissolve and has used that to calculate the KSP. How are these calculations done? Well, whenever we're doing math with Ksp expressions, we have 3 big steps. I call these the big 3. And I want you guys to write these down every time you see an equilibrium expression. The big 3 steps are balanced equation, molar ratio, and Ksp expression. And you pretty much have to do them in order. Now, in the next unit, we're going to be substituting the molar ratio for something called an ice chart. In fact, we'll probably even try a few ice charts in this unit to try to figure them out. But at this point, we're going to keep the simplest version of something called an ice chart, the molar ratio. Regardless of the type of middle step that you use there, you have to start with a balanced equation. How does copper carbonate ionize in water? How does it break apart? Well, the trick is listen to the name. The name is copper carbonate. So it's going to break apart to form copper and carbonate. So here's copper carbonate breaking apart to form copper and carbonate. I can see from my equation here that I've got 1 copper for every 1 carbonate. 1 copper for every 1 carbonate. Remember, on the product side of your equilibria, we have dissolved ions, and ions have charge. We know carbonate has a charge of -2, and since there's only 1 copper, it must have a charge of +2. So when we write these equations out, we want to write them out balancing them. It has to be a balanced equation, but also we have to have the charges included. Now, at this point, that's not going to change your math, but it's a really good habit to get into because in future units, if you drop a charge, it will change your math. Also, this is just correct. This is called an Ionic equation. We didn't write a lot of those in grade 11, but in grade 12, they become really important because they more accurately describe what's going on. So, my copper carbonate is going to be in the form of a solid, and my copper ion is aqueous, and my carbonate ion is aqueous. That's my balanced equation. My next step is my molar ratio. In the molar ratio, what I want you to do is look at the balancing. In this equation, we are balanced. One of these breaks apart to give you one of these and one of these. That's our balancing. We don't know how many copper carbonates are going to dissolve. I know that it's pretty insoluble. We looked at our solubility charts on the bottom of your blue cheat sheets that I've given you. Copper carbonate doesn't dissolve well, so I don't know how much will dissolve, but it won't be a lot. So let's say that X amount dissolves. Well, if 1 dissolves, I get 1 copper and 1 carbonate. So if X were to dissolve, I get X coppers and X carbonates. This is a molar ratio. Underneath each of the 3 species in this balanced equation, I have written a value of x. If, for example, we're going to just change this for a second. If, for example, this was a 2, and of course it's not, but just for giggles at this point, we'll pretend it would be, then we'd have to put 2x here. Now let's just get rid of that because that's going to complicate things. That's not actually how this particular equilibria goes. This one is a 1-to-1-to-1 ratio. It is an x to x to x ratio. Well, what the heck do these x's mean anyway? Well, they mean different things depending on which side of the equation they're on. On this side of the equation, on the reacted side of the equation, x tells us the amount of copper carbonate that will dissolve. And it's telling us that in moles per liter. So we're going to find out the amount of copper carbonate that will dissolve in moles per liter. There's a name for this. The name for this is solubility. Now, I recommend you add these little notes somewhere in your textbook or your note package because this is going to be really helpful for you in understanding how the problem's going. So any value of x that we find that is on the reactant side tells us the amount that will dissolve in moles per liter. It's going to tell us the solubility of that salt. And again, any ionic compound in chemistry is called a salt. Well, what does x mean if we find it on the product side of the reaction? Well, on the product side of the reaction, x tells us how much actually got dissolved. It tells us the concentration of the ions. So x is a stand-in. It's our variable, our unknown for the concentration of the ions that we have here, in this case copper or carbonate, at equilibria. And again, I recommend you guys write this down. Again, concentrations will always be in moles per liter, also known as molar. So lots of my questions are going to say, what is the concentration of copper ion when it's at equilibria? Well, right here we can see the concentration of copper ion is defined as being x. If we know what x is, we know what its concentration is. I might ask you, what is the solubility of copper carbonate? Well, the solubility in this case is also x, because the amount that dissolves, the solubility, is what we call x when it's on this side of the arrow. In this case, the value of it is the same. X is x is x. It isn't always the same, and we'll do some examples of that as well. So from all of this information, we've got a balanced equation, and from that balanced equation, we have a Ksp expression. From all of that, we should be able to write, we have a molar ratio. From all that, we should be able to write our Ksp expression. So let's take a look at how we're going to do that. So the balanced equation gave me the molar ratio. It's also going to give me my Ksp expression. Ksp equals the concentration of my copper plus 2 ions times the concentration of my carbonate minus 2 ions. This expression right here is usually worth a mark on my tests. It's your way of showing that you understand which species are included and which species are not included in your equilibria expression. We have square brackets that are shorthand for the concentration of, and we have the ions involved, so I know which ones they are. Well, we can further simplify this at this point by taking our values from our molar ratio and putting them into the Ksp expression. Right here, I've got the concentration of copper. And right here, we've defined the concentration of copper as x. So I can substitute x inside those brackets. I can say the concentration of copper is x. Right here, we're looking for the concentration of carbonate. And here we've described the concentration of carbonate as being x. So let's also say the concentration of carbonate is x. X times x is equal to x squared. We now have a really simple expression that we can solve. Ksp is equal to x squared. Now, in this particular problem that they've given us, we've done the big 3 steps. We have a balanced equation. We took that balanced equation and figured out a molar ratio. And then we wrote a Ksp expression, what I've done here in blue. I have substituted my molar ratio into my Ksp expression to get a very simple math formula. This is a very simple math formula. Ksp is equal to x squared. Now the question on your screen says, what is the solubility of copper carbonate? Remember which x meant solubility, the amount that can dissolve? It's this one. This is the x. Remember, their absolute value is the same. They'll all have the same number once we figure it out. If I'm being asked to find solubility, I'm looking for x. If they want me to find the solubility product constant, they'll actually use that whole big long phrase, and that's the Ksp, solubility product constant. So in this case, they've given me the Ksp, and at the top of your screen, we can see the Ksp. I mean, I found it on that chart on page 615, not 614 like it says in your notes. The solubility product constant for copper carbonate is 2.5 times 10 to the minus 10. So let's substitute that in there. We know this value, so I'm going to write down the value they gave me. 2.5 times 10 to the power of minus 10. You guys remember when you're using your calculators here, I want you to use your EXP or your EE button in place of times 10 to the power of. At no point do I want to see you pressing buttons on your calculator times 1, 0, power. Don't do that. It'll mess up your calculations. Use your EXP button or your EE button that takes all those places. You'd enter that as 2.5 exp minus 10. So this value is equal to x squared. I've just substituted where I have a number. How do I solve for x? Well, I square root. If this is equal to x squared, then the square root of this value would be equal to x. And if I take the square root of that value, I get 1.58 times 10 to the power of minus 5. That is equal to x. This value is the solubility of copper carbonate. So this value is going to come out in moles per liter, and it will be the solubility of the copper carbonate. We've completed the math, and I've looked at what the values of x means. Let's take a look at another example. In this example, we're going to take a look at what happens when we dissolve lead iodide. When lead iodide dissolves in water, it will break apart. And I would like you guys to pause the video here and try to see if you could write for me, just to start, the balanced equation for lead iodide. You don't need to go further than that. Just see if you can write the balanced equation. Okay, pause the video here, and when you're done, you can continue going. All right. Here we are back with lead iodide. Did you get it right? When lead iodide breaks apart, it breaks apart to form lead and iodide. Think of the name, lead iodide. It makes lead and iodide. Now, if you wrote I2, that's not iodide, that's iodine. And yes, iodine is one of the diatomic elements. But this isn't a molecular equation. This is showing how things break down in water. This is showing how things ionize. Remember, when lead iodide, that orange lead and those two green iodides that I've drawn on your page, break apart in water, water pulls them apart to form one lead ion with a +2 charge and two of the iodine ions with a -1 charge. So this is your proper balanced equation for your lead iodide. And it's a common mistake that a lot of people make. Remember, what we're doing is a dissolving equation. We're not doing a decomposition reaction. All right. Now that you have your now that you have your equation correct, use that to try to figure out for me your molar ratios, your x's, and your Ksp expression. Go ahead and pause the video while you try that, and then as soon as you're done, hit play. Cool. Are you back? With lead iodide, we can see that the balancing is 1 lead iodide breaks down to give you 1 lead and 2 iodides. Now, since we know that a full 1 isn't going to break down, we don't know that. We only know that X amount will break down. X lead iodides then would be X amount of leads and 2X amount of iodides. So my molar ratio is X to 2X. It's not going to be 1 to 1 to 1 like the last one because we're getting 2 iodines here for every 1 lead. So we get that information from my balanced equation. I go back to my balanced equation to try to figure out my Ksp expression. Remember, lead iodide was a solid. In this entire unit, guys, we're going to be dissolving solids in water, so we will never include anything on the reactant side. We'll only be using the product side. So my Ksp expression will be the concentration of my lead ion, right here, times the concentration of my iodide ions. And what do I do with the 2? I square it. I don't go 2i inside the brackets. This 2 becomes the square outside the brackets. Okay, remember what X means in the molar ratio? X here means how much lead iodide will dissolve, the solubility. X here means how much lead ions will I have when the solution reaches equilibrium. 2X here means how many iodide ions I'd have when the solution reaches equilibrium. I'd have twice as many as I have leads. Let's take now and substitute into our Ksp expression, because writing it this way is worth the mark. But now let's do the math. So we're going to take, inside the brackets, I'm going to say, what is the concentration of lead? Well, the concentration of lead was X. So I'm going to put this X right inside the brackets. The concentration of iodine was 2X. And we have to remember to square it. Now here's another place where kids make a bit of a mistake on a regular basis. 2X squared. This 2 squares both the 2 and the X. So 2 squared is 4, and X squared is X squared. We'd have 4X squared times X. We are at 4X cubed. So be careful when we have a square outside of a bracket that has more than one thing in it. We have to apply that square distributed equally to both of them and then multiply by the other one. So we have 4x cubed. My Ksp expression is going to be 4x cubed. All right, so on our chart on page 615, we can go and look up how much the Ksp is for lead iodide. So on our chart on page 415, if you take a look at it, you'll find the Ksp for lead iodide is 9.8 times 10 to the minus 9. So if we have Ksp right here, is 4x cubed. We know this value is on our chart. It's going to be 9.8 times 10 to the power of minus 9 is equal to 4x cubed. What is the correct order of operations here to solve for x? Well, first you divide both sides by 4. So I'll just switch colors here. If I divide this side by 4, to keep it equal, I divide this side by 4. Now I have x cubed. And then to get x by itself, what we have to do is cubed root. So I'll switch colors again so it doesn't get too crazy. We're going to do the cubed root of this side to cancel this cube. So I have to do the cubed root of this whole thing to get this side. All right, we've got a little bit of math to do here. First go 9.8 times 10 to the minus 9 and divide that by 4 in your calculators. Once you have an answer, find your cubed root button and take the cubed root of it. And you're going to get this value, 0.00135, 0.00135 will be equal to x. Or if you have your computer or calculator in scientific notation, that will be 1.35 times 10 to the power of minus 3. And this is actually a more correct way to write it. This value is going to be in moles per liter, and that's going to be x. Now, the biggest mistake kids make at this point is they stop. They've done the math, they have their number, they go on to the next question. At this point, we really have to check, guys, did I actually answer the question? So we're going to scroll right back up and go, what was the question? Well, the question was, and actually it was on the last page, the question was, what is the concentration of lead? Well, when we did our breakdown, we said the concentration of lead was X. And nice for us, we've actually solved for x. So what I should be saying here is, yes, this is the concentration of my lead. This is the concentration of my lead plus 2 ion. I should write that down so that I'm saying, yes, I know what x means. Because what if they had asked me, what is the concentration of iodine? Iodine's concentration isn't x, it's 2x. Had they asked me the concentration of iodine, and they will, we'll definitely have questions where we ask you to solve for that. The concentration of iodine ion, would be 2x. So it would be 2.7 times 10 to the minus 3 moles per liter. So it would be twice as much. So we have to be careful once we've solved for x that we stop. Have I actually answered the question? All right, one more problem. In this case, I'm going to give you one of the values of x. I'm going to tell you the concentration of magnesium, and I'm going to say, go ahead and use that to figure out what the Ksp would be. So now we're going to try to find the other side of the equal sign. We're going to try to find the value for this. This will be our unknown. I'm going to give you one of these values. Now, if you think you can do this, go ahead, pause your video, and try it on your own. If not, follow along, and we're going to do it together. Either way, start with your big 3 steps: balanced equation, molar ratio, Ksp expression. Then, substitute your molar ratio into your Ksp expression so you have a very simple math formula. See if you can try that now. Okay, so here we go. Let's take a look at what we're going to do with this here. We have magnesium hydroxide breaking down to give you 1 magnesium and 2 hydroxides. So I can see from this balanced equation that every time X amount of magnesium hydroxide breaks down, I'll get X amount of magnesium and 2X amount of hydroxide. Remember, the numbers in front of the X's are the same as the coefficients. This is a 1:1 to 2 ratio. So it's X to X to 2X in our molar ratios. Now, I look back at that balanced equation again to try to write my Ksp expression. So here's the money one, here's the mark on a test. Ksp equals concentration of my magnesium plus 2 ion times concentration of my OH minus 1 ion. And remember what I do with the 2? Square it. 2 goes outside the brackets as a squared. Now I'm going to take, and I'm going to keep my brackets here, and I'm going to substitute those values for X right inside the brackets. The concentration of magnesium was X, the concentration of hydroxide was 2X, and remembering that we have to square that there, so X times 2X squared is 4X cubed. So here's our very simple little math expression. We have Ksp equals 4X cubed. Okay, let's keep that even simpler. I'm just going to keep this down here, bring this down. Ksp equals 4x cubed. Now, this question is asking us to find the Ksp. We don't know what this is. Okay, so we do know one of the values of x, though. They told us the concentration of magnesium. The concentration of magnesium is x. So that's easy. Had they told us the concentration of hydroxide, well, that number would have been 2x. We would have had to divide it by 2 to find out how much x was. But they kept it simple for us. They said, here's magnesium. We know magnesium is x. So basically what they're saying is, look, the concentration of magnesium is this number. And we said down here that this number is equal to x. That's what we said when we figured out our molar ratio. So how easy is that? We'll substitute that number, 1.1 times 10 to the minus 4, in place of the x, because now we know how big x is. So let's put that number here. So my Ksp is going to be equal to 4 times that big value for x cubed. That big value for x, we said we figured it up above, was 1.1 times 10 to the power of minus 4. Now, again, order of operations matters, you guys. In your calculators, you should be trying along with me. 1.1, find your x button. So 1.1x minus 4. Enter that in, and then cube that number. Okay, cubes come before anything else. Then multiply by 4. It has to be in that correct order. When you do that, you're going to find that you're going to get a value of 5.32 times 10 to the minus 12. 5.32 times 10 to the power of minus 12. It's a minus sign. That is the value of our KSP. And just like the KEQ unit, we don't write units for KSP values. They technically do have units, but they change for every salt depending on whether we're squaring things or cubing them or whatever. So as a rule, we don't tend to write them down. So in all of our problems that we're going to have that we could give you guys, once we have a formula down to the big 3 steps, we've done our balanced equation, our molar ratio, and our Ksp expression. We've done these big 3 steps. You then get a very simple math formula by putting your molar ratio into your Ksp expression. At this point, you guys, there's only ever 2 questions I can give you. Here's the KSP. You guys figure out one of the x's, or like in this expression, here's the x. You guys tell me what the KSP is. This entire unit really could only have 2 possible questions. There's nothing else we can do when there's only a variable on one side or the other. So it's actually reasonably simple for us to do, to figure out. Okay, now there's a lot of work to learn this, and I've got 3 places I want you to go to practice. The first place I want you to do is go to the end of your workbook, those correspondence pages called Lesson 2. They've got page numbers at the top because I photocopied them out of another booklet. There'll be page numbers 184 to 188. Read through it. Anytime there's a definition, a key term, see if you can write down in your own words a quick note about what it means so that you understand it. Also, do the questions that you find in Lesson 2. Don't worry about going on to Lesson 3 yet. We also have practice for you in your textbook. If you read over pages 614 to 617 in Chapter 17, they're going to explain again more about what I was just talking about. And there are questions 20 through 24 for you to practice in your workbooks. Practice doing calculations for solubility KSP questions, and they're on pages 616 and 617 of your black textbooks. Finally, first 3 pages of your workbook section, so right after the end of the notes, we're only a page or 2 away. The first 3 pages of your workbook section, pages 1, 2, and 3, have a pile of questions. In those questions, either I've given you the KSP and said find x, or I've given you x and said find the KSP. You're going to have to read these ones rather carefully, because sometimes when I gave you x, when I gave you how much dissolved, the solubility, I gave it to you in the form of grams per liter or grams per milliliter. You'll have to remember to change that to moles per liter first. Okay, guys, this is a lot of work, and I'm really planning on you working on it for about 3 days. It would be about 3 class days for that. So expect the next video coming up in a few days. If you've got any questions at all, please make a post or a chat comment on Teams, and we will get to those for you. Good luck.